Welcome everybody. This is Ty Warner with Kissoff Tech Support, Tyka Engineering. It's a division of Gleason Corporation. Today we're going to talk about reverse engineering an enveloping worm set. So a lot of these gear sets were designed back in the 60s, the 70s, and the information they used back then was all hand calculated. Not the same as they are today. They use a lot of tables, that kind of stuff. Well, we're going to try and reverse engineer a set from a couple drawings we got, and the drawings weren't not what I would call stellar, but they're enough to get started. So the first thing we got to do is we got to define what we're doing. We're going to try and figure out the modules or the dimensional pitch, right? And then we're going to figure out some materials if we don't have those, and then verify that this design fits packaging constraints. I don't know what the loads are on this. I do know that I do have some numerical information about what this particular gear set is as far as size, pitch diameter, tip diameter, that kind of thing. Okay, so here we have our Kissoff. I'm going to open this up. Now we're going to start fresh. Alright, a couple of things we do know we have, and that's this information here. Okay, so we're looking at the known information, which is in this bolded information here. We know it's 33 teeth. We have a circular pitch, the tip diameters, the throat centers, this sort of stuff. We think this is the throat radius. I think it might be a little bit big, so we might have to look at that. And we have some worm dimensions as well. We've got the circular pitch. Okay, so there's two ways to calculate this. We're going to go with pi over the circular pitch. We can also go with the number of teeth over the pitch diameter, which is here. But this is a reference, and it doesn't work like that for the worm. Alright, so we're going to go with this top one and assume that this is our normal dimensional pitch. Okay, and we have some other information here. 25-degree pressure angle, tip diameter is 8.0625. We've got face width, and we have an operating center distance. The material is defined here as 4615 and SA65 bronze. Alright, so we know we're going to be, this is axial transverse, alright, and what we're given is the normal dimensional pitch. Actually, we calculated it, and remember what we calculated was 4.375. That's the normal. Okay, so we're going to put in the normal dimensional pitch 4.375 and calculate this. Here's a transverse module. Okay, so we accept that, and I might not want to see that in transverse module. I don't normally want to see module stuff when I'm working in the imperial system, so I'm going to go up here to the module specific settings. I'm going to put input of normal dimensional pitch instead of normal module. I'm also going to check don't abort when geometry errors occur, and the reason I'm doing that is because I don't know exactly what kind of errors I might run into trying to put this together. Alright, I'm going to allow a large profile shift. Okay, is there anything else I want to do in here? No, there isn't anything here. Sizings, no. Calculations, I can calculate with the normal module instead of an axial module, which would be the transverse. What does that change this up here? I don't know. Safety factors, generation, we might have to do something with that, I don't know. So here's my normal dimensional pitch. So module specific settings, input of normal dimensional pitch, don't abort when geometry errors occur, allow large profile shift, calculate with normal module. Alright, we know that's a 25-degree pressure angle. I don't know if I had it in there, but it is a right-hand threaded worm. It's 4 teeth on the worm and 33 on the worm wheel. We know that the worm is 6 inches long, and the worm wheel is 1.625. It's face width. 1.625. Okay. The center distance is 5 inches. They told us that. It was in the drawings. It's a 90-degree angle on the shaft. We really don't need the strength. So I'm going to turn that off because I don't know what the loads are. I want that material change, and I had a 4516, and I want to know what the equivalent of that is. So if I go here and I look at an equivalent chart, I can see 4320 is here, and if I come back into here, I can find 4320 right here. I accept that. And if you didn't have 4320, you can't find it, always go up to your extras, configuration tool, materials, and make sure you're in the AI-SI standard. Alright. Bronze, we said SAE 65. Again, I'm going to look at a equivalent. SAE 65 is a 907, and really here what I'm looking at is this information for tensile and yield. So 4422, 5530, this would be a centrifugal cast. That seems to be the best information for that. So I'm going to go with this 5530, and when I go in here I'm going to just, oops, wrong one, I wanted the bottom one. I'm going to grab this. You can see I've got a 932 in there, but that really doesn't hit the numbers I need. 5530 was the number. So I'm going to grab this top one here. That's pretty close. And this is for the shear fatigue. And that's going to be less than, it's at roughly 50% of the shear strength. So I'm okay with that. And so that'll be my material here. Oil bath, VG220, I'm not going to change that. So this is some information that we just kind of start out with, and we don't have what the load case is. So what we're going to do now is we're going to turn on this tooth form as well. All right. So in the basic data, we have this information we've plugged in. We can run this. We didn't even change anything in the reference profile, and we don't have the right center distance. So nothing worked, right? Well, let's look at the reference profile. We're going to start with the profile A. Let me get rid of this. Right here, and profile A here. But you saw right away that it's telling us, based on the information we have, a 38 in the root is too big. And it says a max at 0.317. So what we still want to stick with a common profile. And if we go down here to this 0.3 for both, we should get rid of that warning, and it goes away. Now it just tells us that our center distance is terrible. Alright. Tolerances, worm according to Neiman, worm wheel according to Neiman, I think those are fine. If you have other tolerances you want to use, feel free to enter those at your own input or whatever. I didn't get an overpin measurement on these, so we're going to go back to the basic data tab, and now we need to size this stuff. And what we need to do is we need to size this based on the operating pitch diameter. So we're going to look at this lead angle at reference diameter right here. We're going to convert this. We're going to select from the reference diameter and center distance. The reference operating diameter, this is for worm 1. This is for the first gear. Okay. 2.458. That's our operating reference diameter, 2.458. So we're going to come back into here. 2.458. We know our center distance is 5 inches, and we calculate 21.8367. We say accept, and now we're going to run this again. Okay, now enveloping worms have a throat radius, and they have some other things we have to define. So now we get this data warning right here. Okay. Well, we can see that the worm operating diameter is 2.458. That's what they gave us. And the worm wheel is 7.542, which is 1/8 thou different than 7.555. But this is a reference number, so I think I'm okay with that. We're going to go back and we're going to look at this a little bit more. So first we're going to go into these details. The throat radius, we said it's 1.222. I think that's a little bit big. The throat center distance is 5. It's the same as the operating center distance for the set. The external diameter, all right, this is for the worm wheel. What do we put here? 8.0625. So we put this 8.0625. We're told there's no chamfer on this at all. So the gear design does not have a chamfer, which is fine. And we're going to run it without a chamfer. So we say none. Okay? We're going to run this. It runs good. Let's look at the graphics on the meshing. Alright. This cannot be calculated. Please run with a tooth form activation. Let's run this. Alright. What does that say again? Define proper value in, DA0. That's right here. I need to get this tip diameter correct. I'm just going to size that. And now we're going to run it. Okay, no failures. The operating diameter looks right. This one looks close enough. Let's look at the meshing. Here's the mesh. Here's the worm. Here's the worm gear. And let's see, what do we see here? The worm diameter is 2.914. And the worm wheel is 7.998. So the worm wheel at 7.998 is small. And the worm diameter at 2.914, where does that look here? 2.915, it looks correct. Yes? I'm good with that. So we hit the right diameters. It looks like we've hit the right pitch on here. And this is what that should look like. I will tell you that we're going to have to make this worm wheel diameter a little bit larger, 8.0625. And there's a couple places we can do this, but I recommend we do this in the reference profile right here. We can change this to own input. Okay. And we're going to look at this addendum coefficient. The addendum coefficient for the reference profile is the tip diameter, 7.9991. We need to make this 8.0625. And if we calculate that and accept it, we're going to get this warning. So we've got 0.0248 clearance instead of 0.03. I don't know if that's a problem, but you can see this is the actual diameter of the worm wheel, because now it's 8.06159, and we need it to be 625. Okay. And the worm diameter at 2.914, 2.915, it's pretty close. So here is the design at this point. Well, we got to check that 3D information first, but right now this is like, okay, I could buy that this is the design. You can see that there's no backlash in here at all whatsoever. And so there's going to probably have to be some information played around with in order to get the proper backlash that we want in the set. And that could be we make some changes here or there in order to get it. So if we were to do another look at this, and let's say that, and they didn't tell us in the drawing, but let's say this is actually transverse. This is a transverse right here. And this shouldn't be the normal pitch, it should be the transverse or the axial. And if that was the case, we'd go up here to our module specific settings, change this off of here, and you can see our transverse dimensional pitch is off. And if we run this, you can see how things are a little different, right? Our worm gear diameters change and our worm wheel diameters change. And if we take this back to 1, alright, 8.03, that's pretty close, and 2.949. But remember, we calculated that, and we calculated 4.375. Okay, we need to size it again. 2.548, I think is what it was. 458 with a 5-inch center distance, and then we have this lead angle. Okay, and now we have what I think looks like a much better gear design. The teeth are much better proportioned right here. We still have the right diameter here, 2.91455, but now our worm wheel is off, 7.99824. Okay, transverse. We go back to reference profile. We're going to go to this addendum coefficient right here, and we're going to make this 8.0625. You can see it changes that right there a little bit. We run this is going to get taller, and we're not going to have enough meshing. That's a little bit pointier tooth. But this is the design. This is the diameter, and this is the right diameter for the worm, 2.915. And we can play with that a little bit. So if you wanted to make sure it was exact, you'd go to own input, 2.915, it's there. That looks just like a rounding thing. Okay, so here's a mesh. Doesn't look too bad in my opinion. Looks pretty good. Let's look at the 3D graphics here, and let's look at the worm wheel. I don't know what this is going to look like yet. We defined that throat radius. I looked at it from the drawing. It could be big. To me it looks a little bit big. We'll let this calculate here in a minute. Alright, so our gear, our worm wheel calculated, and that does not look right. It doesn't look right on the drawing. So we obviously have too large of a throat radius here. We know the throat center is good, so let's just let's try this at 1.1 inch. That looks big to me. So at 1 inch, let's see what this does. Alright, so it calculated, and here is our new geometry, and when I look at the drawing or I look at the actual gear in hand, this looks like what it ought to look like. It looks like the actual gear. And if we look at the 2D geometry for meshing, this looks alright as well. We've got some backlash here. Let's go ahead and just make a flank contact to the left. Now let's go to the right, I guess. There. We've got contact here and here. So what's our ratios are? So here's our mesh. There we go. We're going to try to balance this out a little bit. Okay. Now you see I got sharp edges on this worm, and the drawing says that I need to have rounded edges. The edges need to be broken off and not sharp. So I'm going to go to my modifications tab right here, turn this on, and then for the worm I'm going to add rounding. I'm going to click my little plus button here, and I'm going to give it 15 thou round on that tip. And now when I run this, well, crap, it's going to take a little bit, but we'll let this calculate. Alright, that calculated through, and now you can see I've got a little bit of rounding here. I broke this edge. You'd have to look at the gear and decide if this 15 thou is enough. If I wanted to make this and just see the final, I'd have to turn this properties tab on and then go to this worm, turn the original off, and now you can see my round. Okay, and you can see, turn that off, and you can see the whole mesh here. Okay, so here's the mesh. I think that looks pretty good on a 25-degree pressure angle tooth. I don't know what this backlash is just yet. I'm going to look it up here in the report. This 3D model looks really good. I think this matches the gear that we had in hand. So that is good. So we can turn that off. What we're going to do is run the report right here, the main report. And if you don't get the report up in this window, you can go to the report settings and make sure you turn this external editor on. Alright. So here's our report. Let's see, I have it unnamed, and that's fine. So messages, did we get any? Well, we had this message, gear 2 does not have enough tip clearance. Well, it still has tip clearance, 24 thou versus 32 thou. So maybe that's not a problem, but again, we're just trying to make sure these gears match what we had in hand and what was on the drawings. There are things we can do here to fix that. We don't have any collision, so that's good. We're using this only geometry calculation. We're using the ISO 14251, which is fine. We have a ZK flank, all right, and there's lots of different flank designs for a worm gear. If we were to look at this here in the details, here's the shape of the flank, right? ZI, ZK, ZA, ZN, ZH, and if you were really interested in those types of things, what it meant, you can go to search and type in ZK. Worms. So this goes over the types of flank forms, right? And you can go right down through this in the settings and try and figure that out. So it depends on how you cut it. It depends on how, you know, if it's an involute, if it's concave, convex, that kind of stuff on these tooth forms. ZK is the default. All right. So you can change that if you need to. And of course, it's not defined on the drawing. Very rarely was it ever defined on the drawing. So let's look at our drawing here. Our information. I'm gonna go ahead and display the full page width. We have our information here, our transverse, normal, and normal diametral pitch. Okay, here's our normal pitch, here's our transverse. Usually worms are defined in transverse or axial pitch, which is why I switched it in the middle there. We have our normal pressure angle, our lead angle, the number of teeth, the hand, okay, face width for the calculation. Here we have our materials, the reference profiles. So this is a standard profile, so you have to be able to find a cutter out there somewhere. And this PF max, or ROF P max, is the maximum root diameter, or the root radius factor that would fit without collision. All right, that's what that means. Information on your final machining, and then here you've got details for manufacturing the worm, throat center distance, face width chamfer. This one didn't have it in that case. External diameter, tip diameter. All this information is here. And as we come down here a little bit, this is the worm wheel. So you have the tip diameter here, tip clearances. Here's my diameter. Here's my profile shift. Right here. Transverse module. Let's see, I'm looking for this tip diameter right here. 2.9151 and 8.0, and then here's my manufactured. Here's my tip radius, tip diameter, tip form diameter, tip diameter allowances. Maybe a thou is not enough. Maybe you need 5 thou. I don't know, but it's just I went with that. And if you wanted to change this tip diameter allowance, it's easy enough here in the tolerance tab. You just click this on, and you can change them right here. Easy enough. I don't think that this actually has a center distance allowance of 0.8. I'm probably going to change this over, and maybe it's 5 thou for this size of gear, right? Because I don't know. I still don't have to worry about this tip clearance. I still got clearance. And now my report's a little bit different. It's not too bad, but here down for the tooth thickness now, I get my backlash free center distance, and then I have my theoretical ball over pins and my normal tooth thickness, normal backlash. So my normal backlash is anywhere from 2 thou at min to 14 thou at max, but that assumes you have a full plus or minus 5 tolerance on here. So here's the design. And did it actually work out? Let's see, did our up here for the pair, we want to see the values here. So our dimetral reference center distance, okay. There was an effective tip, reference diameter, base diameter, tip diameter was good. The generating is good. I'm looking for my reference operating diameter right here, 2.458, that's correct, and 7.542. Okay, it's not 7.555, it's 1/8 thou off, but that was a reference on the drawing. So this is probably as good as it's going to get. They could have done something crazy with their design to throw people off, but who knows. So this is a pretty good reverse engineered gear set at this point. I'm going to save it, save file, save as, and again, you should save early and often. I'm going to save this as a just a training example, right? And then you guys can, if you're following along with this stuff, you can save if you want. It's a pretty good example for the worm reverse engineering module. Okay, let me save that. All right. If you have questions, feel free to email me or respond on the KISSOFT USA channel. Feel also free to subscribe and like. If you want a sample or if you'd like to try the software, email me ty.warner@kissoft.com. I'll get that email and I can send you out a 30-day trial for the full software. Other than that, it's a nice example. If you have questions, again, like I said, get in touch with me. Go ahead and respond to the YouTube channel, and hopefully we'll see you again on some future video chats. Thanks for watching.